Hi, I'm Paul Fagerburg.
I'm Jack Rosenthal, and we work on the Chrome OS firmware team at Google. We're here to talk to you today about Zephyr on our embedded controllers. So you may or may not already be familiar with the existing embedded controllers inside of Chromebooks. Essentially, the functionality of the embedded controller is to handle low-level tasks, often when the system is powered off. Things like the keyboard, turning on the main processor, delivering power through USB Type-C and charging the battery, as well as potentially any sensors, buttons, switches, etc. And initially, way back in the days, Chromebooks used a proprietary vendor-provided embedded controller that Google didn't have access to the source. And it was very difficult for us to maintain. Not only did we not know the security of the controller, but oftentimes bugs would be impossible to debug for us. And so with the Google Chromebook Pixel or Link and the Samsung Chromebook with Snow, we developed our own open source embedded controller. And we've been using open source embedded controllers on most all of our Chromebooks since then. And so the URL is there to our existing embedded controller code base. But back then, we didn't have access to a great open source real-time operating system like Zephyr. So we wanted to go into that. So while our existing OS, which is homegrown, meets our needs technically, it's actually a wonderful OS to work in my opinion. The issue is that being our own custom OS with custom chip support and SoC support, we find it very difficult to collaborate with external contributors because oftentimes they were looking to just write the code for their chip once and not again specifically for Chromebooks. So what you have to realize is oftentimes Chromebooks have a similar model being produced by the OEM for a proprietary operating system instead of Chrome OS, and that oftentimes they need to do the embedded controller twice during the development process, once for Chrome OS and once for the proprietary OS, which is a lot of work on all of our vendors, including SoC vendors and chip vendors.
So we did some research and some proof of concept work. After that, we decided to focus on the Zephyr project. The Zephyr project is a fully open source RTOS. It includes support for a lot of microcontrollers, and the safety and security are designed into the OS, not bolted on after the fact. Google had a press release at the end of September. We joined the Zephyr project as a platinum member. We are very much looking forward to working with the strong community of experts and participating in this organization and pooling our efforts for chip and platform support into just one RTOS kernel. So Zephyr brings us several benefits. First and foremost, as I mentioned, is this large community. There's very strong industry momentum around Zephyr. Intel, NXP, Nordic Semiconductor, Texas Instruments, Sci5 are all making a lot of commitments into Zephyr. It's fully open source, and our support for Zephyr builds on Google's commitment to the open source community. Neutral governance encourages broader community participation, and the security is a very important consideration. We want to protect the user's data. Good security is an absolute requirement, and that's not to say in any way that there was an insecurity in our current EC kernel. It's just that if we can't move to something else if we have to sacrifice security in the process. And so having that open code with the security model in there enables us to make that move without sacrificing security or putting the user's data at risk in any way. And then there's a lot of technically cool stuff. These are things that we're not using right now, but we could use in the future, like multi-core support for ARM's big dot little chips, memory sandboxing for continuing safety to make sure that code can't interfere with other code, and different options for scheduling algorithms as well, if that were something that we wanted to look into in the future. Lots of neat things in there. So on the flip side, what Google brings to Zephyr, we have big plans for contributing to Zephyr and encouraging others to contribute. We have a standards compliant USB-C power distribution stack. There is a robust test suite for it, and we also have detecting quirks of a lot of popular chargers that aren't 100% compliant, and we need to do one small thing to be able to interoperate with that charger. So we've got a lot of that knowledge that we've developed over the years. We have chip vendors. We're bringing others along for the ride. There are chip vendors who are adding support to Zephyr upstream because they want Google to use their chips, SoC vendors as well. And then we have Google engineers actively participating in working groups, in code review and design reviews. So I'll hand it over to Jack to talk about our technical aspects of our transition.
All right, so transitioning to an entirely different operating system for your embedded controller is no easy task. And our goal in this transition is not only to reuse our existing code as much as we can, but also to continually develop on top of the new features that are landing inside of our existing code base. Obviously, we can't pull the plug all at once, so there's plenty of new developments happening in our existing embedded controller code base right now we'd like to take advantage of. And how we're doing this is that we're adapting the existing code for our embedded controller to be compiled as a Zephyr module, so that to Zephyr OS, our existing code base just looks like a module and can be loaded into Zephyr OS as well. And we've created header files and various runtime adapter layers, which actually allow the existing code to run on top of Zephyr's APIs. So an example of how we do this is on this slide. Here we have a declare console command macro, which allows our existing code base to define console commands for the debug console on the UART. Zephyr has a separate shell subsystem that we want to take advantage of when we're using Zephyr OS, and it has a slightly different API. The macro is called shell command register, and the parameters are slightly different. But in the header files that we've developed for our shim layer, it can adapt the existing macros that we're using in our code base to fundamentally use Zephyr macros and allow our existing code base to seamlessly work as Zephyr code.
So also as part of our transition, we are moving our unit tests over with the actual task code in the runtime. We've got that translation layer that Jack talked about. For the unit tests, we're actually changing the code to use the Zephyr Z-test API and then building it directly for the native POSIX target to run on the host. We also want to be able to build for EC's host target as well. And so we have a compile time translation layer that lets the Zephyr Z-test API compile into our EC test API and then build directly for that host target. So the benefit there of moving the unit tests over to the Z-test API is to make upstreaming our code much easier. We can move code over to Zephyr, but if the unit tests don't run in the Z-test API, then getting that accepted upstream is going to be much harder. It's much, much better to provide those unit tests already in the Z-test API. And that concludes our presentation. Thank you.